When splitting your data into training, validation, and testing sets, it's important to first randomly shuffle the observations in your data. Let me give you a quick example as to why this is important. Let's say that you are creating a classification model that is intended to diagnose individuals as having a certain medical condition or not, based on measurements taken from blood work and other sorts of medical tests. Let's assume that you've collected information on 1,000 individuals, 100 of which do have the medical condition, and 900 of which do not have the medical condition. And let's say that when the data was collected, whoever collected the data arranged it in the data set so that the first 900 rows of the data set correspond to the individuals who did not have the condition, and the final 100 rows are for the individuals who do have the condition. So let's say the data set comes to you, and then you first split it into training, validation, and testing sets according to an 80-10-10 split. And assume that you do not shuffle the data. And in fact, you just take the first 80% of the observations, or the first 800 observations, and assign that to the assign that to the training set. Then you take the next 100 observations, assign that to the validation set, and the final 100 observations, and assign that to the test set. Well, the final 100 observations were the only ones corresponding to individuals that did have the medical condition, and those all went into the test set. So when you train your models on the first 100 observations, none of those individuals had the condition, so all of your models are going to simply predict nobody has the medical condition. They will get 100% accuracy on the training set. Then they will get 100% accuracy on the validation set, where, again, nobody has the medical condition. But then when you apply these models to the testing set, for which everybody has the medical condition, your models will get 0% accuracy. So for this reason, you want to always randomly shuffle your observations before splitting the data into training, validation, and testing sets. Python provides convenient tools for doing this manually, but fortunately, Scikit-Learn provides a function called train test split that will actually do this shuffling for us. The use of this function is illustrated in the next cell, where we perform an 80-10-10 split on our iris dataset. So let's walk through this code. So first off, we will import from scikit-learn.model-selection, we will import the function train test split. So this is the function that will do our splitting for us. Now we're actually going to apply this function twice. Whenever you use this function, it splits into 2 pieces, but we actually need to split our data into 3 pieces. So we're initially going to split out the training set, which will consist of 80% of our data, and then we will leave the other 20% in something we're calling the holdout set. Then, as a second step, we're going to split that holdout data set into a validation set and a testing set. Okay, so let's walk through how that works. Ignore the stuff on the right for just a moment. Ignore the variables on the left for just a moment. So here we're calling train test split. We're telling it we have to provide it with both our features, which are stored in X, and our labels, which are stored in Y, because each of these arrays, each of these objects have to be split in a consistent way. Then we are going to specify the test size. So in this case, that's going to be 20%. Now, the test size in this case refers to the holdout data set. So we're going to, basically this just says that one of our data sets is going to contain 20% of our observations, and then the other data set will contain 80% of our observations. This splitting is done at random, but if we want the results to be reproducible, we have to specify a random state. This random state can be any integer that we want, any positive integer that we want. I'm simply going to specify 1 as the random state. This is basically setting a random seed prior to performing the splitting. Okay, so this function, train test split, returns 4 objects. It returns features for the training set. So in this particular case, this will contain 80% of the data, 80% of the feature information. It will return the features for the holdout set. So this will contain 20% of the features. Then it will return the labels for the training set and then the labels for the holdout set. Okay, so after running this cell, we will have our training labels in xtrain. We'll have our training features in xtrain and our training labels in ytrain. But we need to further split the holdout set. So we'll do that in a second line of code. Here, we're going to call train test split. We're going to split xhold and yhold, and these need to be split equally. Now, xhold contains 20% of our original data, and we want the validation and testing sets to each contain 10%. So we're going to split xhold and yhold 50-50. So we'll use a test size of 50%, and then you can specify a different random state here. But again, for the sake of reproducibility, we will specify some random state. We'll just select one. Okay, so xhold will be split 50-50 into xvalid and xtest, and yhold will be split 50-50 into yvalid and ytest. Now, let's print out the shapes of each of these 6 objects that we've created: xtrain, xvalid, xtest, ytrain, yvalid, and ytest. Okay, so recall that our data contained 600 observations originally. If we put 80% of those observations in the training set, we will have 480 observations. So xtrain has shape 480, 4. 480 observations, 4 features. 10% of the original 600 would leave us with 60 observations for the validation set. So we can see that the shape of the validation set, xvalid, is 60, 4. 60 observations, 4 features for each observation. Similarly, the shape of xtest is 60, 4. The labels, y, were a one-dimensional array. So when we split them, we're going to get one-dimensional arrays. Ytrain will contain labels for 480 observations. Yvalid will contain labels for 60 observations, and ytest will contain labels for 60 observations. It should be pointed out that this training, validation, test set approach is the most straightforward method of estimating a model's out-of-sample performance. However, it does have a few issues in that the results you get depend very heavily on what observations go into the validation set and what observations go into the test set. If you repeat this process and get a different validation and a different test set, that can actually dramatically affect the model's estimated out-of-sample performance. As it turns out, more sophisticated methods do exist. In particular, there's a method called k-fold cross-validation that tends to produce better estimates of a model's out-of-sample performance than this standard training, validation, test set approach. However, this particular approach is much simpler to understand, and it is where we will start in terms of evaluating our model's out-of-sample performance.